Good morning. In this lecture, we will discuss NMR Spectra Analysis. Means which main things that we have to note down from the NMR spectra to find the structure of the organic compound. And side by side, we will discuss that which information, which parameter we are going to note from NMR, and with that parameter give which type of information. So when NMR spectra is in front of you, you have to see the number of peaks. Each different kind of hydrogen give a peak or group of peak. So when you counted the number of peaks, suppose there are 4 peaks. It means in your organic compound there are 4 different kinds of hydrogen atom. Like each different type of hydrogen give a different peak. So if there are 4 peaks in a spectra, it means the number of different kind of hydrogen atom are 4. And this is basically how to find, suppose organic compound is there in front of you, how to find out that how many different kind of protons are there. That concept is called equivalent or non-equivalent proton, that we will discuss shortly in this lecture. So first thing that we have to note down from the NMR spectra is count the number of peaks. How many peaks are there? Suppose there are 5 peaks. It means in your organic compound there are 5 different kinds of hydrogen present. So number of signals or peaks, that is equal to number of different kinds of hydrogen atom in the compound. If there are 9 peaks, it means there are 9 different kinds of hydrogen atom in their compound. Okay, different kind means non-equivalent. And how to find now non-equivalent, that we will discuss shortly. Second thing which we must note from the NMR spectra is the value of chemical shift, as we discussed in the previous lecture. The distance from TMS in ppm. So what information that chemical shift provide, that is the types of hydrogen generating peak. Means there are different types of hydrogen, like hydrogen present in alkene, in alkane, in alkyne, in alcohol, in ether, in ester, in aromatic compound, etc. They give different chemical shift. So from the value of chemical shift, like it is 2.0 ppm, it's a 5 ppm, suppose it is a 7 ppm, then that 7 ppm value is for aromatic hydrogen, aromatic protons. So there are specific values for every type of organic or functional group. So from the value of chemical shift, we must see what is the chemical shift, what is the value of chemical shift for a particular type of peak. And from that value we come to know which type of protons that may be. Third thing that must we note from the NMR spectra is the area, or that is called integral. Area under the peak. Like this is a peak, okay, and this is a smaller peak. This peak has more area as compared to this peak. So what the area of peak, area under peak or area under curve give information that provide us the number of protons. If suppose there are 2 peaks, if there are 2 peaks in the NMR spectra, it means we have 2 types of hydrogen atom in the compound. Now what is the number of these 2 types? How many hydrogen are there of type 1? How many hydrogen are there of type 2? That will come to know from this area. The length or the height of the peak, that give information the number of hydrogen atom. More the height, more the number of hydrogen causing that peak. So this integral of peak we must know to find out that how many protons, equivalent protons collectively causing that peak. If the area under curve is more, means height of the peak is more, that you can compare from here. This peak, the height of this peak is more, it means this peak is given by more number of hydrogen atoms, almost double number of hydrogen atoms as compared to this second peak. Okay. So first information, that's only about the types of, that there are different 3 types of protons. Now 3 types of proton means there may be a group like 5 protons are one type, 6 protons are one type, 2 protons are one type. The number, that how many protons are of the same type or are equivalent, that is given by this integral of peak. Next is spin-spin splitting. Like it's not necessary that all the peaks are like these, that single peak. They may split. Like sometimes the peak may split into like this. This is, you can see, it's a triplet. 3 means triplet. Sometimes the peak may split into doublet. Sometimes the peak may split into quartet. That we will see how the peak will split and what is the rule. That's n+1 rule is there. So splitting, spin splitting, that give information about the number of hydrogen atoms on the adjacent carbon, both sides. Okay. Splitting of the peak totally depends upon the number of hydrogen present on the adjacent carbon. So spin splitting, we must note whether the peak is singlet, whether the peak is doublet, triplet, multiplet or quartet. Okay. In detail we will discuss spin splitting in this chapter also, this chapter only, how the splitting take place and which factors that cause the splitting of split peak. Last information that we get from the NMR spectra is coupling constant. Coupling constant is just a distance. Like if we have a, suppose this is a triplet, 1, 2, 3 peaks. One peak split into 3. So this distance, this distance or this distance is always constant. That is called coupling constant. Coupling constant, it gives information about the axial and equatorial type of proton present in the molecule. Okay. So one by one we will discuss all these things, don't worry at this stage. At this stage you just try to understand that what information we get from the NMR spectra and how to analyze the NMR spectra, which parameters we must note down to find out the structure of organic compound. Like each parameter gives some information about the structure of the organic compound. We must note these things. We must count number of peaks, we must see the chemical shift value, we must see the height of the peak, we must see the splitting, whether it is doublet, triplet or quartet, and we must note down the coupling constant. So these 4 or 5 parameters, they give these informations, and from this information we can easily find out the structure of our novel organic compound. So this is about the shielding and de-shielding. We will try to understand what is shielding and de-shielding. Now this is the NMR spectrum, how it looks like. It looks like that there is a TMS at the far right side where value is 0 ppm, as we already studied. Towards TMS we have a higher field, because when we move from left to right, the external magnetic field strength that increases. Higher field means higher external magnetic field strength. So when you move towards TMS, means towards TMS we get the signal that will be at higher field. Those are called shielding. And when the signals are appeared at this end, that is called de-shielding. Lower field. Lower field means lower magnetic field strength. The signal appeared. You can compare it with this. Like this signal A, C. This signal is at higher field. Signal A is at lower field. Means when we apply as external magnetic field strength is less, we get a A. Little bit more, we get a B signal. Little bit more, than we get a C. Means when we increasing the external magnetic field strength, first we get signal A, then we get B, then we get C. You can say the signal C is shielded. Here we require more strength of magnetic field. So keep in mind, when there is a shielding, we require more strength of magnetic field. Signal A is de-shielded, then we require a less strength of external magnetic field. See what is shielding and de-shielding. Now this is any nucleus, and in nucleus we have a proton. Okay, and that proton has a magnetic field. That magnetic field interact with the external magnetic field. Then only the signal appeared in the NMR spectrum. But this proton is surrounded by some electron cloud. And you know, electrons are also charged particles. They also have their own magnetic field. So these electrons, as the more dots means their electron density is more as compared to this. Here around this proton or this nucleus, electron density is more. Here around this proton or this nucleus, electron density is less. So when there are more number of electrons and each electron have its own magnetic field, that magnetic field interact with the external magnetic field. We are applying external magnetic field for nucleus only, not for electron, because we are going to study protons. But when you apply external magnetic field, the magnetic field of electron that interact with the external magnetic field and shield the nucleus. They just like they shield the nucleus from this external magnetic field strength. So to make this proton which is present in the nucleus into resonance, we must apply more external magnetic field, then only that proton comes in resonance with the radio wave frequency. Okay, it means this is shielded. That's called shield. That's why in shielding we require strong magnetic field strength. Like shielding is this side towards TMS. Why we require strong external magnetic field? Because electron density is more around the nucleus, around the proton, and these electrons they have their own magnetic field, so they just shield the nucleus from the external magnetic field. So to make that proton which is present in the nucleus into resonance, we must apply stronger magnetic field, because opposing power is there, opposing tendency is there. But if the electron density is less, by some way or other we withdraw these electrons away from it, then electron density decreases. When the electron density decreases, then the external magnetic field strength also decreases, because now the proton present in the nucleus, it can feel the external magnetic field. So we do not require too much strength of external magnetic field to make that proton into resonance. So we require a small strength of external magnetic field. That is called a de-shielding. You can see here, de-shielding, lower field. De-shielding takes place at lower field. Okay, so this is all about the electron cloud. If around the proton the electron density is more, then that signal of proton will go towards TMS, means shielding. That proton will not come in resonance at lower field strength. We must apply a strong external magnetic field to make that protons into resonance with radio wave frequency. And if the electron density around proton is less, they can easily become in resonance with the radio wave frequency wave at lower field strength. Like see in this example, this is ethanol. In ethanol you can see the proton A is attached with O. Okay, it means around the proton A the electron density is less, because suppose here is A. This is your proton. This proton is A. Okay, and now this oxygen withdraw electron toward itself, because oxygen is more electronegative than hydrogen. So when the oxygen withdraw these electrons, then this shielding that decreases or finish. The electrons which are present around this proton, which are opposing the external magnetic field, now this electron cloud is attracted by the oxygen. So when it is attracted by the oxygen, then we require very low field strength to make this proton into resonance. That's why the signal of A appear at this side. Okay, now you can compare B and C also. To B, proton B, there are two protons in B. The oxygen is attached to a carbon, that oxygen is attached. But this oxygen is far away from this C protons. It means at C proton the electron density will be maximum. At B the electron density will be less. At A electron density will be minimum. So depending upon the electron density, these protons they come in resonance at different field strength. Okay, so external magnetic field that we are applying, that is uniform. That is uniform over the entire molecule. So it cannot make different protons are non-equivalent. However, the magnetic field that is induced by the movement of electron over the molecule is not uniform. Here you can see in this molecule, here the electron density is more. Here the electron density is little bit less. Here the electron density is again less. So this movement of electron or this electron density that makes the difference. Otherwise, our H naught is same. We have a molecule and we are applying magnetic field strength. So our magnetic field strength is equal for all the protons. But what makes the proton different is the electron cloud around those protons. And if the electron cloud is more, as you can see in this molecule, electron with these black lines, they show the electron cloud. And you can see here that electron cloud is not uniform over the molecule. If it is uniform over all the molecule, then only single peak will appear, no problem. But in a molecule, whether it is a small molecule like this ethanol or a very big molecule, the electron density is not uniform. And that electron density makes the proton non-equivalent. The part of the compound, suppose this is the compound, it's a big compound. This part has a low electron density. There will be de-shielding. And here electron density is more, here electron density is more, so this part of the compound gets shielded, requires high electron, a strong magnetic field, means the peak will appear towards TMS. So in this way, all the protons present in the molecule, they have a different electron cloud around them. That makes them different. Their behavior different toward external magnetic. Otherwise, external magnetic field strength is uniform. We are starting from one point, continuously goes on increasing from left to right. Okay, but when you apply a magnetic field, it is uniform for all the compounds. You can't say that magnetic field applied here is more as compared to here. No, it's uniform. But how the protons give different peak, that depends upon their electron density around them. If there is the more electron density, that proton gets shielded. That proton will not come in resonance until high magnetic field is applied. That's why the proton C, you can see that these protons C, they appear towards TMS, means upfield. And proton A, where the electron density is less, they appear far away from TMS, that is called D-shield. Okay, so this is shielding and de-shielding which makes the difference, which is the basic concept of NMR. And basically what the compound, we can say that we said that there are three types of proton in the ethanol, A, B, C. Why they have a different types of proton? Why we call it A, B, C a different? Because they have a different electron density around them. This is the only electron density around the proton which makes the proton non-equivalent towards external magnetic field, and due to which different peaks appear in the NMR spectrum. Next we will see, we will learn how to find the number of peaks or number of signals given by the molecule. If molecule is in front of you, you can easily detect how many types of non-equivalent protons are there. And non-equivalent protons, number of non-equivalent protons equal to number of peaks. Because number of non-equivalent proton means they have a different environment. They have a different electron cloud environment. That's why they come in resonance with radio wave at different field strength. Okay. So next in topic we will learn how to find the equivalent and non-equivalent protons. This is a number of signals, peaks, that's equivalent and non-equivalent protons. So if there is a different connectivity, they give the non-equivalent protons, and non-equivalent protons means number of peaks. If in a compound there are 5 non-equivalent protons, it means there will be 5 peaks in the NMR spectrum. If the connectivity is same, we will say they are equivalent protons. All the equivalent protons, whether they are 2, 3, 4, 5, 10, 12, 13, 14, they will give only one peak. All the equivalent protons give one peak. When the protons are non-equivalent, they give different peaks. Let's see with a lot of examples. For example, first compound is, say, methane. There are 4 protons and all the protons have the same connectivity. You can see all the protons are connected to carbon. This is also connected to carbon. This is also connected. You can say all the protons are connected to methyl group. Okay, so like this, This proton is connected to methyl group. This proton is connected to methyl group. So all the protons have a same connectivity. It means this methane give one signal. We will mark it A means all are equivalent. So give one peak only. If we move towards ethane, so first we will compare these three protons, whether they are equivalent or not. Then we compare with the other three protons. So let's open the structure. First compare these three protons. Okay, I will make them blue. I'm going to make them blue. Okay. So these three protons, blue one, see their connectivity, whether their connectivity is same or different. This proton is connected to carbon with two hydrogen, and this carbon is connected to methyl group. This proton again connected to carbon with two hydrogen and methyl group. This proton again, it means all these protons, these three protons, they have that same connectivity. Similarly, all these three protons, they have the same connectivity. Now if we compare two protons on adjacent carbon, just compare these two, whether they have the same connectivity or different connectivity. They have the same connectivity because this proton is connected to this CH2 group and CH3 group. This proton is connected to CH2 and this CH3 group. It means all these six protons, they are equivalent. Again, this compound gives one peak. In this way, you have to compare. Okay, now the next is CH3, CH2, CH3. If you open up this structure, you will get structure like this is propane. First compare these six hydrogen. These six hydrogen, 3 on one carbon, 3 on last carbon, they are equivalent. You can compare their connectivity. This proton and this proton and this proton have the same connectivity. Okay, these three protons, they have the same connectivity. These three protons, they also have the same connectivity. Now compare intercomparison. These two protons also have the same connectivity. It means these six protons have the same connectivity. You can mark them as AA. But what about the other two? These protons, this proton and this proton. Now compare these two protons. This proton is connected to C, further C, but this proton is connected to C and both side carbon. Different. So both are different. It means these two protons on the central carbon, they are non-equivalent. They are different from these six protons. So we will mark it a B. So it means 6 protons give one peak, 2 protons give one peak, the total number of peaks are 2. So in the NMR spectra, this compound gives 2 peaks, 1 by 6 carbon and 6 hydrogen and 1 by 2 hydrogen. And their intensity will also be in the 1:3 ratio. Like this is due to 2 protons, and this is goes like this and like this. You can see here intensity. Intensity is in the ratio of 1:3. This is because of B, this is because of A. So this is integral part of the NMR spectra, that from the height we can get information that peak A is because of more number of protons as compared to B, and by knowing the ratio you can find out that they are in the ratio of 1:3. Okay, next example. Next is we'll take butane, CH3, CH2, CH2, CH3. So how many types of protons are there? You can see these two protons are equivalent. Their connectivity is same. These protons are connected to carbon and then this whole group, propyl group. These three protons are also connected to carbon and this propyl group. These two protons and these two protons are equivalent. You can see they are equivalent. Just let me explain by opening this structure. These three protons are of methyl. These two. This molecule is quite symmetrical, you can see here. Okay. Now these three protons are equivalent with one another. These three protons are equivalent with one another. Now compare these two. These are also equivalent. They are also equivalent. Okay, now compare these. This proton and this proton. They are equivalent. You can see this proton is connected to carbon, this side, and C, this side carbon. This is also the same environment. These protons are also equivalent. These, you can compare these, they are also equivalent. You can see this proton is connected to carbon, this side methyl, this side ethyl. This proton is connected to carbon, this side methyl, this side ethyl. Same. It means we have two signals. 3 proton, 3 proton. 6 protons give 1 peak. These two, 4 protons give 1 peak. So total 2 peaks will be there in the ratio of 2:3. Okay, next example. CH3, CH2, 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 propane. Now, see this structure. If we compare the connectivity, first open up the structure to better understand the concept. Do it carefully and slowly by understanding each and everything. These 3 protons are equivalent. Compare with one another. These 3 protons are also equivalent. And now if we compare this proton with this proton, they are also equivalent. You can see. Here it is connected to C with 2H and this group, butyl. Here this hydrogen is also attached to C with 2 hydrogen and this group, equivalent. It means you can put here A and A. 6 hydrogen give 1 peak. Next, move to next. These 2 protons are equivalent. These 2 protons are equivalent. They are also equivalent. Compare it. Where this proton is connected to C. This side methyl group, this side propyl group. This proton connected to C. This side methyl group, this side propyl group. Means same. It means these 2 and these 2 are equivalent. These 4 protons give 1 peak. Now what about these 2? They are equivalent. These 2, they are not equivalent. You can see their connectivity. So it means this will give C. So this compound give 3 peaks. So this is the general idea to find out the number of peaks in a given molecule. Okay. Next example. If we take CH3, CH2Br, how many types of protons are there? Ethyl bromide. Open the structure. Okay, now compare. These 3 protons are equivalent. This proton is connected to carbon, Br. This proton is connected to carbon, Br. This proton is connected to carbon, Br. Equivalent. But when you compare these proton with this proton, they are not equivalent. You can see this proton is connected to carbon and this carbon is connected to carbon, which is connected to bromine. Directly you can see here that this proton is more close to bromine and as compared to this. So this carbon is connected, hydrogen is connected to carbon directly to bromine. It means you will get two signals, A and B. 3 protons give one signal, 2 protons give one signal. So here will be 2 peaks. Can you think about their position in the NMR spectra? Which side will be A, which side will be B? As Br is more electronegative, so it will draw the electron density where the electron density will be less. At B or A? At B. So means B will be de-shielded. So B will be like in this side. So this is your B, this is your A. So this is particular, you can think about the position in the NMR spectra also. Why B toward down de-shielded? Because here the bromine is directly attached, it decreases the electron. Here the electron density will be less. So these two protons, they come in resonance at lower field. Lower field this side, left side. Okay. Okay, in next example, suppose we have a ring. Here we have fluorine. Here we know that there are 2 hydrogen on each carbon. How many signals this compound will give? See, these 2 protons are equivalent. These 2 protons are equivalent. See this. Now compare these. Intercomparison. This proton and this proton, they are equivalent. You can see that this proton is connected to carbon, which is connected to CFF. Again, this is carbon to CFF. Same thing. It means these give is signal 1. These protons are different, but they are same. These 4 are same. They will give us different peak. And these 2 protons at the bottom side, they are different from our, they give C. So this molecule will give 3 peaks. So in this way we will follow this, that different connectivity has non-equivalent protons and same connectivity has equivalent protons. Same connectivity means same connectivity of this and this. It means all these protons have the same connectivity, so these 3 protons are equivalent protons and equivalent protons give single peak. But if you compare these 2 protons, connectivity of this proton and this proton is different. It means this proton and this proton are non-equivalent, they give different peaks. So in the next lecture we will discuss a number of more examples and to find out number of peaks in each and every compound.